Hey guys, so we're going to take a look at gases next. So a couple of things. First of all, uh, gases are very different than any other phase of matter. We talked about solids and liquids, but gases are completely kind of in their own separate category. They don't interact with one another. They just kind of bounce off one another. And most importantly, is pressure is a thing. Because there is a lot of space in between them, we have to kind of consider what pressure is and how these things work. So normally for a liquid or in a solid, here's a solid. It's a bunch of atoms really close together. They're really ordered, and that's what you get. So that would be solid. For a liquid is different because we have essentially they are very close together, but there's a lot of disorder, and these things are allowed to move. So they're all over the place, but they're allowed to kind of shimmy about and exchange partners, not like a solid. A solid cannot change partners. That would be a liquid. But a gas is a little bit different. So a gas, let's pretend we have a lid on here. We can put lids on all of them, but it doesn't really matter. So a gas is just going to be kind of on its own, filling the entire space that it has. So these things are going to be going at pretty fast velocities. They're going to bounce off the walls. They're going to run into one another, and the others, they're going to send them off. They're going to run into each other and exchange energy. So there's a bunch of things going on. But that's kind of what liquids, gases, and solids look like. Liquids and solids are interacting with one another. Gases are not. Gases run into one another, but they fly off and do their own thing. So gases just kind of are all over the place. So when we're looking at gases, we talk about the kinetic molecular theory of gases. Essentially, kinetic being motion, the motion of molecules in gases. So how do they behave in the gaseous state? So first of all, gases consist of particles that are in constant random motion. So they're just moving about as randomly as possible. They're doing whatever they want to do. They're going to go in a direction until they run into something. And that's pretty much it. So it hits a wall, bounces off in some other direction, runs into another molecule, transfers some energy, and that's how gases work. Second, gas particles are colliding constantly with each other and the wall. So when a gas particle bounces off the wall, it applies a little force to the wall and it heads off in another direction. But these collisions are elastic. Elastic means that there is no energy loss. So if I have two things coming together and they collide, when they bounce off each other and head back out in whichever direction they're going to end up going in, they're going to have the same energy that they came in with. So let's say that this one is traveling at 100 miles per hour, meters per second, and this one was traveling at 5 meters per second. The end result is the other one could be leaving at, let's say, 90 meters per second, and this other one would be heading out at 15 meters per second. As in, when they collide with one another, they head off in the opposite direction with the same energy transferred between the two of them. All right, so gas particles are small. The total volume of their container, essentially what we're saying here for number 3 is if I have a container filled with gas particles, in actuality, if I isolated this and I turned it into a liquid, the gas would be just a small little droplet in the corner. So the gas particles fill the entire container, but the actual volume is minuscule in comparison to the container that it's in. So if you think about all the gas particles that are in the room that you're sitting in right now, if you shrunk them down, you could compress them into a liquid and it would be no bigger than, a tiny, cup of water or something like that. So it's a very small amount of stuff. So overall, the space is negligible that the gas actually takes up. So that's why we don't ever consider that when we're looking at certain volume considerations. 4, there are no interactive forces. They're not going to attract one another. Again, I said that when they run into one another, they just kind of transfer energy and off they go, right? So what happens is they run into one another. There is no attraction. They're not going to hold on to one another at all. They just kind of head off in opposite directions. The average kinetic energy of gas particles is proportional to the absolute temperature. So the hotter something is, the faster particles are moving. So increasing in temperature equals more motion. And that's it. That's the idea here. The hotter something is, the more energy is in the particles. Okay, so the faster they're moving on average. Some can be moving really slowly, some can be moving incredibly fast, and there's some average energy. Ultimately, the hotter it is, the faster they're moving on average. Okay. All right. So enough of that. Let's take a look. I want to kind of go through pressure somewhat. I know I talked about this in class, but units of pressure. So if you look at if we're at 1 atmosphere of pressure at sea level, what that ultimately means is there is 1 atmosphere pushing down on our heads. The weight of every single molecule above our heads, all of the gas, is pushing down on us and keeping us, essentially, that's what's holding us down, or that's the weight that we're feeling on top of our heads. So pressure is measured in force per unit area. So force per unit area. Force being the weight of all of the particles and all of the molecules on our head, per unit area, the mass of my head, for example. Okay, so the masses are the amount of force pushing down per how much space it's actually being forced onto. And that, your book kind of does a neat little thing, and I'm not going to go through all the conversions here, but ultimately, if you think about this, an elephant versus an ice skater, force is equal to pressure is equal to force over unit area. Pressure is equal to force over some specific area. If you think about an elephant, the force is really large. It weighs a lot. There's a huge mass pushing down because of the amount of mass that we have. So really large mass equals a very high force. But the area is actually pretty small, or pretty large, considering they have 4 feet, right? 4 feet. And their feet are pretty big. So they're big feet being pushed down. So that actually we have a large area too. So overall, the pressure pushing down, the elephant is feeling on the ground is not as big as we would expect for such a large animal. But if we look at something like a figure skater has a very small mass for the most part. And definitely not as large as an elephant. So the force of them is smaller, but the amount of area, the width of the blade is very thin. And this woman here in this picture is on 1 blade. So 1 blade, it's, I don't know, a centimeter across and 10 centimeters long. All of her weight, her 100 some odd pounds, is pushing down on the ice in a very small area. So in this case, we have a very small area and a reasonable size force. And so you have to consider the amount of space that all of that pressure is pushing down is really increasing pressure. So there is a lot of pressure on there. There's a lot of pressure on that 1 foot, as opposed to the elephant was 4 feet. It's well distributed. And that's what we see a lot, is the distribution of mass, or the distribution of force, is important. So we got a bunch of different units of pressure. I highlighted the important ones, so I'm just going to highlight them again. Atmospheres, you need to know this. And this conversion right here, and I'll write it below as well. 1 atmosphere is what we see at room temperature. Torr and millimeters of mercury, these two are equal. These two are the same thing. 1 torr equals 1 millimeter of mercury. So you can kind of use them interchangeably. Torr is equal to a millimeter of mercury, but ultimately the Pascal is actually the unit of the metric system uses. But the ones that we're going to focus on are atmospheres, torr, and millimeters of mercury. So the important unit here is 1 atmosphere, all lowercase. 1 atmosphere equals 760 torr, which is this because of the same thing, 760 millimeters of mercury. Okay, so those are the important conversions to know. You'd always get those, but torr, millimeters of mercury are the same. Atmospheres is kind of the one that we default to for the most part. So why do we use millimeters of mercury? So when you have a barometer is essentially, again, it's measuring pressure. So it takes this small little, large surface area, and we usually fill it up with a liquid. So we're going to fill this up with a liquid. I'm going to erase that. There we go. So if we fill it up with something like, let's say, water, and you take and put in a upside down capillary tube, and that upside down capillary tube is filled with vacuum. So whatever it happens to read, that level right there is the pressure. And now what you have is the pressure of the atmosphere is pushing down on the liquid. And because the liquid that's pushing down on the liquid, it's forcing it up into that tube, that inverse capillary tube. And so we measure the pressure of the atmosphere by seeing how high that goes, right? The greater the pressure, the higher that's going to go, the higher the pressure that's going to be. The less pressure, the lower this thing is going to be. So we can always measure it that way. The reason that we use mercury is because of how much it weighs. If we use mercury at atmospheric pressure, we end up with a column of mercury that's about 2.5 feet, okay, under vacuum. So 2.5 feet. If we use water, we have something that is 34 feet in height. Okay, you're not going to create a barometer with water, although it's safer technically than mercury because mercury seems scary, but I don't want a 34-foot instrument in my lab. Let's just use something like mercury. So that's why it works. How do you measure blood pressure? So blood pressure, again, it's force that we're measuring, force per unit area. So normal blood flow, we have just blood flowing through the arm. You pump up the little cuff in order to cut off all circulation below where you put the cuff. We call that a blood occlusion. And essentially, you should not hear anything when you put the stethoscope right underneath the cuff. And slowly you let that pressure drop. And as soon as you can hear something, the force of the blood going through, you're finally hearing the remnants of some kind of blood making it through. The force of the blood is greater than the force of the blood is greater than the force that's keeping it closed. So the cuff is pushing in and the blood pushing through. As soon as the blood can force its way through, you start to hear stuff, and that is the systolic pressure. And then when you can no longer hear any changes, there's the diastolic pressure. So you're actually measuring the pressure at which it forces its way through the arm. And of course, that's a good way to measure blood pressure because we're comparing the force of the cuff versus the force of the blood pushing through. But again, force per unit area, depending on how big your veins are and whatnot. All right. It's used in climatology, and meteorology. There's a huge portion of pressure. If you look at the atmosphere, it's made up of a bunch of different layers, all at different pressures. The troposphere is where we live. The stratosphere, mesosphere, we're seeing less and less pressure as we go up because there's less and less air. There's less and less pushing down on that spot. So that moves us to the simple gas law. So pressure is important. That's kind of the end result. And we do these things in lab. So I'm going to kind of, you can usually think these things through. So the Guy-Lussac law is basically saying pressure and temperature are going to affect each other. So as we increase temperature, we see an increase. As we increase in temperature, we see an increase in pressure. Okay. So increased temperature equals an increase in pressure. That makes sense. Volume, again, I'm going to go back to PV equals nRT. If I am changing pressure and temperature, volume and N are staying constant. So we're keeping everything else constant as we go through this. And we'll talk, PV equals nRT is our ideal gas law, and we'll talk about that in a bit. So increased temperature equals an increase in pressure. These two are inversely, or they are proportional to one another, I should say. So one changes, the other one's going to change in the same direction. Increased pressure, increased temperature. Increased temperature, increased pressure. Charles' law, and again, I'm just running through these because I'll show you the combined gas law as the relationship between the two of them. Charles' law says, if I increase the temperature, we're going to see an increase in volume. Okay, again, assuming pressure remains constant, increasing the temperature is going to increase volume. It's going to create more space, right? Those molecules are moving faster. The faster these molecules move, the more they're putting more and more force on that little plate. The plate is going up to maintain the same pressure. And slow moving molecules, fast moving molecules, they need more space to spread out, and they're going to push that thing up. It's the volume. All right, next up, Boyle's law. Volume and pressure. So again, Boyle's law, if I'm going to decrease the volume, according to our picture here, we are going to see an increase in pressure. Decreasing the volume pushes them closer and closer together. It's causing more force. The bouncing is happening more and more often. It's causing more pressure. And so we see that volume is inversely proportional. Volume is inversely proportional to pressure. So if pressure goes up, volume goes down. If volume goes down, pressure goes up. So they're going opposite directions. Okay. That's in fact how we breathe, is taking advantage of changes in pressure. So if you stop breathing, the pressure outside of your lungs and inside of your lungs are equal. Okay, so that's your pressure. You will always see something go from high pressure to low pressure. In fact, air will always flow from high pressure to low pressure. So if you open a window, it's inside, it's high pressure because it's higher temperature, right? Increased temperature, increased pressure. So inside right now, it's warm probably. And if it's in the winter, it's warm and there's a higher pressure inside. So as soon as you open the window to the outside, to the cold, the air is going to rush out. Although it's going to feel like cold air is coming in, actually air is rushing out because you have a higher pressure inside than you do out. And that's why you see high pressure to low pressure. And the same thing for lungs. So if you, as the diaphragm contracts and expands, okay, we're going to see that it actually opens up the lungs and increases volume. We see an increase in volume in our lungs. That means we're going to see a decrease in pressure. So if we see a decrease in pressure, this is inhaling. So increasing in volume, the pressure is we're going to see the transfer of gas to the inside. We're going to see gas go from outside higher pressure to inside our lungs because we've just expanded the volume. And then if we reverse directions, so if we relax the diaphragm, we're going to exhale. So we're decreasing the volume, which equals an increase in pressure because we have a bunch of molecules there that don't belong and we're reducing the space. That is an exhale. So all our lungs are doing, taking advantage of Boyle's law, right? Changing in volume equals the change in pressure. Change in pressure gradient is going to allow air to flow in and out of our lungs. And then finally, Avogadro's law. We don't change molecules much, but if we do, in fact, add gas, what we do see is the more stuff we have there, so more moles equals an increase in volume. So moles and volume are proportional to one another. So the more stuff we have, the more space we need for it, essentially. Again, pressure and temperature are remaining constant. Good. So that brings us all to nothing really to memorize other than this. Okay, this right here, P1 V1 equals P2 V2 I'm sorry, P1 V1 over N1 T1 equals P2 V2 over N2 T2. This is the combined gas law. We have two gases, and what you're looking for in problems are two gases, or I'm sorry, two different states. That gas. So the question ultimately is, did the conditions change? As in, did pressure change? Did temperature change? Did the number of moles of gas change? If anything like that happened, we're using the combined gas law, right? So did the volume change? Did the pressure change? Did the temperature change? Did the number of moles change? If it changed, if one of those changed, then we're using the combined gas law. We are using the ideal gas law at any other point. We use the ideal gas law when we're in a situation where we have one gas and we want to know ultimately what it comes down to for this is we have pressure, volume, moles, and temperature because R is a constant. Okay. In fact, I'm acting like you guys know this, so let me go through. So the ideal gas law is PV equals nRT. P is going to be pressure in atmospheres. It's really important that they all have the units that they're supposed to have. Volume is V, and it's going to be in liters. N is always moles, and it's actually going to be measured in moles, MOL. We're going to talk about R in 1 second. And then finally, T is going to be temperature. And temperature is going to be measured in Kelvin. You must have an absolute unit. Okay, so do not, here's what I said. You must have that in degrees Kelvin. Okay, R is the ideal gas constant. It is 0.08206 liter atmospheres, liters times atmosphere, all over moles times Kelvin. Okay, so that is the ideal gas law. You will always be given the ideal gas law, and if you ever forget what units you need your temperature, pressure, moles, or volume to be in, just use R. I need liters, atmospheres, moles, and Kelvin. Okay, okay. So the types of problems that you would be given for this is you would be provided the three of the pressure, volume, temperature, or moles, and asked for the fourth. So I'm going to give you three. You're going to be asked for the fourth. And there's a bunch of different ways that we can ask that. But ultimately, that's how the ideal gas law is going to work. I have a gas at pressure, this, volume, that, and temperature, that. How many moles are present, right? Some combination of those things. So that's important. All right. So next up, standard temperature pressure, STP. STP is this. We need something to have standards. Okay, so standard temperature pressure is 273 Kelvin, which is 0 degrees Celsius, and 1 atmosphere, the pressure at sea level. Okay, so standard temperature pressure is 273 Kelvin and 0 atmospheres. We need these standards when we're comparing gases to one another. If I want to know the density of a gas, I can't compare the density of a gas at different temperatures. I have to say, well, the density of nitrogen versus oxygen at standard temperature pressure. So we have these standards just so we can compare things together. At standard temperature pressure, and so the standard molar volume of a gas, this sounds fancy, but it's actually pretty simple. So the standard molar volume of a gas is basically 1 mole of any gas at standard temperature pressure is 22.4 liters. So that's a conversion. So now at standard temperature pressure, we know that 1 mole of something is equal to 22.4 liters. Why is that important? Well, we could use this as a conversion factor, 1 mole over 22.4 liters, or we could say 22.4 liters is equal to 1 mole. So we can use this in stoichiometry, which we're going to get to next. So if I give you a reaction that produces a gas and it produces X volume of gas, we can figure out how much stuff reacted. Okay, so it gives us moles, which is important. We don't need to memorize this or anything. In fact, if you plug the values in to PV equals nRT, and you're usually provided this anyway. So pressure being 1 atmosphere, we're solving for volume. 1 mole is my mole quantity. R is 0.08206 liter atmospheres per mole times K. And then temperature is 273 Kelvin. I had some water there. 273 Kelvin. If you solve for volume, you're going to find out that it's 22.4 liters. Okay, so you can always solve for it using PV equals nRT if you need to. So that's the standard molar volume. So the applications, we're going to talk about stoichiometry. I don't think I have it on here. We do it in class. But the application of this is you can determine moles from a volume. That's the important part of this. So if you're given a bunch of conditions, what's the volume? Well, you can figure out moles. Moles will tell us what's going on in a chemical reaction. And from there we go. Okay. So whenever we're trying to solve a problem, we always want to look at, we always want to be able to look at what we're looking for. So in this case, you might be given a problem. In fact, let me give you just some random problem. And I have no idea if this is actually going to work, but the numbers may be a little bit off. But let's say that I have 0.0231 grams of a unknown gas. The gas is at has a pressure of 0.721 atmospheres, a volume of say 10.0 liters, and a temperature of 300 Kelvin. What is the molar mass of the gas, of the unknown gas? So there's a bunch going on here. All right. So let's just first, we should always do this. So when we have a problem like this, we're going to say, all right, let's figure out what information I have. I have 0.023 of an unknown gas. So that right there, that's a mass. My mass is equal to 0.0231 grams. Okay. What else do I have? A pressure of 0.721 atmospheres. So pressure is equal to 0.721 atmospheres. What else? Volume of 10 liters and temperature of 300 K. So again, I'm just pulling out this information. Volume is equal to 10 liters and temperature is equal to 300 Kelvin. I'm looking for the molar mass. So that's what we're looking for. Do we know? So we can always, there's a lot of information here. So the question is, what are we actually trying to solve for? But what we want to do is we want to find what we're looking for and see what we need in order to get it. So I need to get the molar mass. So I need to know molar mass, and I know the unit for molar mass is going to be in grams per mole. So I need a mass in grams, and I need moles in moles in order to solve this. Do I have either of those? Well, let's see. I am looking for this. I do actually have mass, and I do not have moles. Okay, so I can already plug in my mass of 0.0231 grams. So I can just plug that right in. Okay, so 0.0231 grams, and I have to solve for moles. So what happens is, if we know we're looking for molar mass, this is how we solve for molar mass. I already have the mass. If I have the number of moles, I can plug it in here and I can solve for my problem. So we're dealing with gases. When we're dealing with gases, we know that we can use the ideal gas law. There was no mention of any other states. There's only one volume, only one temperature, only one pressure, and therefore we can use the ideal gas law to figure out the fourth. So let's see what we got. So do I have pressure? Yes, I do have pressure. Do I have volume? Yeah, I do have volume. I don't have moles. In fact, moles is what we're looking for, though, isn't it? We have R and we have temperature. So if we can solve for moles, we can take moles and we can plug it in here. And when we plug it in there, then we can solve our problem. Okay. So again, look for what you're looking for and then use the equations to figure out what you need. So I'm going to rearrange this, and this is how I prefer to do it. Moles is equal to pressure times volume. I'm just simply going to divide both sides by RT, okay, to move RT to the other side. So pressure over volume, R over T. My pressure is 0.721 atmospheres times my volume of 10.0 liters. R is 0.08206 liter atmospheres per mole K. And my temperature was 300 Kelvin. Okay, so there we go. Let's do some work here. So I'm going to look at units separately. So let me just do units over here. We can always, we have atmospheres times liters up top divided by liter atmosphere times atmospheres times K. So there's a lot happening here. I can simply say this K is, can extend this times Kelvin times 1, right? So I could just extend that. So this is what we have. Whenever we run into this situation, I'm going to take this and I'm going to keep it. So I'm just going to rewrite it. Take the fraction and I'm going to switch from division to multiplication. And then in order to do that, in order to be allowed to do that, I'm going to take this and I'm going to flip it. So now I'm going to have moles times K all over liters times atmospheres times Kelvin. And so now I can cancel my unit. Atmospheres on the top and on the bottom, liters on the top and on the bottom, K on the top and on the bottom. I end up with just moles left. So once I do the math. Okay. All right. So let me see here, calculator. And so now we just have to do the math. And so here we go. 0.721 times 10.0. So 7.21. Yeah, 0.721 is equal. Okay. So on the top, I've got 7.21. On the bottom, I have 0.08206. And in fact, this is how I would ultimately do it. So 0.721 times 10.0, 0.721 divided by 0.08206, and then divided by 300. You can just do them in individual steps. So my moles is equal to 0.29287, so 293 moles. That's my final answer. And then we can just simply plug this in 0.29. Oh, I think I screwed this up. I'm going to change my math here. Let's say that we had 1 gram of the substance, 1.023 grams, because otherwise it doesn't make any sense whatsoever. So let's say we have 0.293 moles in the bottom, 1.0231, again, I changed the answer, is 0.293, gives me a molar mass of 3.49 grams per mole. That's solved. Having a mass and having essentially moles allows us to get that out of there. Okay, so yeah, so that's it. Application of the gas law, and I think that'll do. Yeah, so hopefully this helped.